So here we go with part 3. Now part 3 I think lays the foundation for part 4, so I'm going to take time to do this. The specifics of this are not on the AP test, but I think it's nice foundational knowledge. So we're going to spend just a little bit of time talking about the Schrodinger's wave equation. The Schrodinger's, that equation is a kind of a nasty wave equation. It looks kind of like this, and so another variation of it is this. So it's kind of a scary looking thing, kind of scares me too. But the thing about it is I want you to notice it gives a three-dimensional component. So derivatives, this is sign for derivative, and psi, it has to do with the amplitude of waves. And so we're really talking about waves and their amplitude. Remember, amplitude is the distance from the zero line in 3 dimensions. You got the x dimension, the y dimension, and the z dimension. So this wave equation generates, the subparts of it generate variables that we in chemistry know as quantum numbers. There's a little discussion of this starting on page 324, and it's a pretty short discussion, just like a half a page. So you might want to read that and then move on up through page 326. But I wouldn't don't get too bogged down in the information that follows, other than you need to know it, but you don't need to know it in that much detail. So here we go. So the Schrodinger wave equation generates 4 variables that are variables that have different values. They are n and l and m and s. And I'm going to talk about each one of these variables and what they represent. They're going to have numerical values in most cases, except for n. The numerical values are not really important, but the number of values is. So here we go. So n can be from 1 to infinity. So it can go forever. But for practical purposes, it only goes to 7. And n represents the main energy level. So if I say n equals 1, that's the first energy level. If I say n equals 4, I'm talking about the 4th energy level. All right, each n value can hold electrons. So in the first energy level, there are 2 electrons. In the second energy level, there's 8 electrons. In the third energy level, there could be 18 electrons. And the way we determine that is the number of electrons is equal to 2 times n squared. So quick, if we're talking about the 4th energy level, that'd be 2 times 4 squared. How many electrons? So you could end up, nobody answered me. Of course, there's nobody in the room. So that'd be 32. So 4 squared is 16 times 2 is 32. So in the 4th energy level, there'd be 32 electrons. All right, so that's the primary. I always mention that this represents the distance from the nucleus. So the n is like the distance from the nucleus. In the picture that I showed you earlier, that being that little animation, let's just go back and take a quick look at that. See if I can got that still pulled up here. I think I do, right here. Okay, so this is n equals 1 right here. This is n equals 2, n equals 3, n equals 4, n equals 5, n equals 6. So those are the main energy levels. So distance from the nucleus. N equals 6 is further away. All right, the L quantum number represents the sublevel, and it has values from 0 to n minus 1. So this is the energy level. N is the energy level. Whoops. Energy level. And L is the sublevel. Okay, it goes from 0 to n minus 1. Now, that means that it can have the number of values of L is limited based on what n is. And I'm going to make a little chart down here for you in just a second. The number of values of L represent the number of sublevels. So each energy level, except for the first one, is divided into sublevels. All right. So let's make a little chart. So what that means is, suppose I was talking about n equals, let's do this, do n and L. So if n equals 1, then L has to equal 0 because it goes from 0 to n minus 1. If n equals 2, then L would equal 0 or 1, because it can go from 0 to n minus 1. If n equals 3, L could equal 0 or 1 or 2, because there would be 3 values, 0 to n minus 1. If n equaled 4, then L would be 0, 1, 2, 3. There'd be 4 values for L, so there'd be 4 sublevels in the 4th energy level. These L values have names. When L equals 0, we always call that an S sublevel. When L equals 1, we call it a P sublevel. When L equals 2, we call it a D sublevel. And when L equals 4 or 3, we call it a F sublevel. And after F, they go alphabetical, G, H, I, and so on, but we never get that high because no atom is big enough to actually have electrons in those sublevels, unless the electrons are excited and have moved far, far from the nucleus. Then they can't stay there, they just come back down. All right, now, so the number of values is the number of sublevels. That's a big deal. So in the 2nd energy level, there's 2 values, 2 sublevels. The 3rd energy level, there are 3 values, 3 sublevels, and so on. Now the 3rd quantum number, M, the M quantum number deals with the number of orbitals. Number of orbitals. Okay, it can have values from negative L to positive L, including zeros. Now again, it's not the numerical value of the quantum number that makes a difference. It's how many values. So the number of values equals the number of orbitals. All right, so the name of this is called the magnetic quantum number, and it deals with the orientation of the orbital in space. I'm just going to put relates to X, Y, Z axis. All right, so let's make a column for M. So if L equals 0, since M can equal negative L to positive L, M can only equal 0 because there's no negative 0, there's no positive 0, it's just 0. Same thing here, that's 0. But if L equals 1, then M equals negative 1 and 0 and 1. And that's why in the class yesterday, there are these 3 orbitals. So let's just take a quick look. Just happen to have that pulled up right here. So in this little movie, we started with the N equals 1. That's this. So N equals 1. The S sublevel, that would be L equals 0. And then we went to 2nd energy level, L equals 0, which is called the S sublevel. Notice it just looks like the 1st sublevel, except it's bigger. So all the S's look alike, they're just bigger as you go higher from the nucleus, or further from the nucleus. Now we're going to go to the 2p. So let's take a quick look to remind ourselves what 2p looks like. And I think I forgot to share my screen. So I might just back up on that just a second. So let's back up, go back to share screen, close this out, go here. That's Yahoo Finance. Stock market was up today, maybe. All right, so this is where we were a second ago. So now you can see it. So we start with N equals 1. And that's this right here. So N equals 1. And L would equal 0 when we're talking about an S sublevel. So now we have N equals 2, L equals 0. N equals 2, L equals 1, and the X value is the M value. So let's remind ourselves what we're talking about, like I started to do a second ago. So the S sublevel was this little spherical shape, the S bigger spherical shape. Now we're looking at the P's, and there will be a P on the x-axis, and that's this value, a P on the y-axis, and that's this one, and a P on the z-axis, and that's that one. All right, so let's go back and take a look at that again. So now moving on. This is the n equals 2, L equals 1, m equals 0 value, because that's on the y-axis. And n equals 2, L equals 1, m equals positive 1. It's on the z-axis. So now we're finished with the second energy level. It had the 2s and the 2p, and in the 2p there were these three orbitals. So now we go to the 3s. n equals 3, L equals 0, m has to equal 0, so we don't have an x, y, z component. Okay, this is n equals 3, L equals 1, m equals negative 1, because that's on the x-axis. Then same thing, except now we got m equals 0. n equals 3, L equals 1, m equals 0. And then n equals 3, L equals 1, m equals positive 1 for the z-axis. Now we're not finished with the third level, but the fourth level comes in. We'll get into that in the next video. So the fourth level begins, and that's n equals 4, L equals 0, and m equals 0 too. Now we get into the d's. Now the d, let's take a quick look at our quantum number possibilities. So if we go to the third energy level, we have m equals 0 for L equals 0 there, because it's just negative L to positive L. This will be negative 1, 0, and 1 again, but this will be negative 2, negative 1, 0, 1, and 2. So there are 5 values. So 5 values means there's going to be 5 orbitals. So here we go. Go back and take a look at it. We'll see those 5 orbitals. All right, so there's one of them. That's the negative 2 value. It's on the x-axis. Now this is just one orbital. It's kind of complicated, and that would be the negative 1 value. And that's on the x and the y-axis all at the same time. So you see how it goes here and here. Then we have the 0 value, and this one's going to go between the x and y axes. So you see how the lobes end up between the axes right here. See, that's between over here. Then we go to the n equals 3, L equals 2, m equals positive 1. And that one goes between the y and the z axis. You see how it fell in between what goes between the x and the z, I'm sorry, between the red and the blue. And the next one goes between the y and the z. And that's between the green and the blue. So this is n equals 3, L equals 2, and m equals positive 2. Now for those of you guys that are purists, the actual x, y, and z is a relative thing, and so I'm using negative 2 for x, negative 1 for y, 0 for z. And I think whatever order I said, the order is arbitrary. So we'll call negative 2x and so on. Negative 1 would be x squared, y squared, and then we'd have the x, y, and so on. So it's a relative thing, which m number we assign to which orbital, because if you just look at it from the other side, the orientations will all change. They'll still be on the axes, but the axes will have a different frame of reference. All right, so after we get to the third energy level is where this video stops. But then we go to the 4s, and it would just be a bigger sphere. And then you'd go to, after 4s, you'd go to, no, not 4s, 5s. You go 4s. And after 4s would be 3D, we did that. Then 4p would be next. 4p would be the next one. Then it'd be 5s, and then 4d, and so on. All right. So that's a little bit about quantum numbers. Now, one more thing. In each one of these orbitals, there can be 2 electrons, and that's the s orbital. Okay, in the s orbital, that's the spin quantum number. Okay, so spin. S stands for spin. And in each orbital there can be 2 electrons. So and one of them spins clockwise and one of them spins counterclockwise. So clockwise, counterclockwise. Here there'd be a clockwise, 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 and then we'd have counterclockwise, counterclockwise, counterclockwise. And the numerical value is 1/2, but you just need to know positive means clockwise and counterclockwise, or negative means counterclockwise. All right, and I also don't know if you noticed it or not, but I put in the positive, 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 and a negative, negative, negative. And the reason for that is that when you put the electrons actually in the orbitals, they spin the same way first, and then after they all have one electron in an orbital, then they come back and they pair up. All right. It's kind of interesting that you can use 4 quantum numbers to describe a single electron, any single electron in an atom. So maybe I'll just show you that real quick. Suppose we're looking at an oxygen atom. So an oxygen atom would have the 1s sublevel, then it would have the 2s sublevel, and then it would have the 2p sublevel. It looks like this. All right, in the 1s, since oxygen has 8 electrons, there would be an electron here and an electron there in the 1s, and that would hold 2 electrons. And then in the second energy level, you would have the 2s, and it would have 2 electrons in it. And each orbital can hold 2 electrons, and since the s sublevel only has the 1 orbital, the s sublevels only get 2 electrons. For those of you who remember the sunny room and the pink room, the sunny room had 1 bed with two people in it, and the pink room had 3 beds, see, 1, 2, 3, with 2 people per bed. So for oxygen, we would have a person in that bed, and a person in that bed, and a person in not that bed, well, it could be that bed, person in this bed, and then you start pairing up. So you'd have a pair here. If you drew it a different way, the 1s bed had 2 people in it, the 2s bed has 2 people in it, the 2p had 3 beds, and the people like their own bed until they have to pair up. And so that's another way to draw it. So if we were going to, we'll call this the second electron, this one right there. So if we were going to put our quantum numbers down for that, we would say N is 2 because it's in the second energy level. L is 1 because it's in a p sublevel. M is -1 because it's the first one of these 3 orbitals, -1, 0, and 1. And S, since it's the second electron in, would be spinning counterclockwise. And so those 4 numbers would describe the electron here in this orbital. It's one way to think about it. Okay, I'll stop it there. That's a little background on quantum numbers. There's some questions about quantum numbers in the assignment that I left you. If you want to, I didn't assign them, but they're on the same page, the same link. So if you want to try some, that might be fun.